Hello everyone. So today's topic is about modern asynchronous counters. Now in the previous lectures we studied about the shift registers, we studied about the counter basic, we studied about the type of counters, that is the synchronous counter as well as the asynchronous counter, which were based on the way in which clock was provided to them. We have learned that in synchronous counter all the flip-flops are fed with the same clock, whereas in asynchronous counter the output of one flip-flop is basically served as clock to the successive flip-flop and so on and so forth. Now counters were basically employed to count clock pulses. However, there is something which is called a mod counter, and that can be applied, that can be rather obtained using both asynchronous counter and synchronous counter configuration. So today we are going to study the modern asynchronous counter configuration. My name is Shiv Charan Puri, Assistant Professor, PC Department, Asansol Uni College. But the question is that the number of states we have seen, or counting sequences rather, through which a particular counter advances before returning once again back to its original first state, that is called a modulus. In other words, the modulus is the number of states the counter counts and is the dividing number of the counter. Okay. So an n-bit counter will have n flip-flops and 2 to the power of n states, and divides the input frequency by 2 to the power of n. So we know this, that a single flip-flop divides clock frequency by 2. Hence it is divided by 2 to the power of n minus 1 counter, mod counter. It can count in binary from 0 to through 2 to the power of n minus 1. A counter that goes through all the possible states before starting is called the full modulus counter. However, a counter in which the maximum number of states can be changed is called a variable modulus counter. A counter may have a modulus less than 2 to the power of n. This is possible with the help of an additional combinational logic. So suppose if it is a 3-bit flip-flop, you can count 8 clock pulses, but even you can go for mod 6 counter. So that's what. This type of counter does not utilize all the possible states. Some of the states are skipped. The number of flip-flops required to construct a modern counter equals the smallest n, for which n is less than equal to the power of 2n. Now what does it mean? For example, if the desired modulus is 10, so suppose n is equal to 10, the smallest integer greater than equal to 10, okay, which is also an integral power of 2, is 16. Okay. The number of flip-flop in this case would be 4, as 16 is equal to 2 to the power of 4, which is equal to 16. So as you can see here, now how to obtain the mod in asynchronous counter, rather how to design a mod in asynchronous counter configuration. So we will first look into the methodology. Okay. Now first step is to determine the minimum number of flip-flops so that n is less than 2n, and connect these flip-flops as a binary ripple counter. Find the binary number for n. Identify the flip-flops for which output Q is equal to 1 when the count is n. Choose the NAND gate with the number of inputs equal to the number of flip-flops for which output Q is equal to 1. As an example, if the objectives were to design, suppose you want to design a mod 11 counter, then in the corresponding count, that is 1011, okay, there is 11, 3 flip-flops output are 1. The desired NAND gates would therefore be a 3-input NAND gate. Okay. So at this particular state, we have to make special arrangement. We will be discussing next that we have to use an AND gate, or rather a NAND gate, and we have to connect the outputs in a specific configuration to reset it to 0. Connect the Q outputs of the identified flip-flops to the input of the AND gate, as I told you, and the NAND gate output to asynchronously clear our inputs of all flip-flops. So that means at that particular time or at that particular clock, everything should be 0. So we have to put all the inputs to the 0. The example is a mod 6 asynchronous counter. So it can count straight from 0 to 5 and again back to 0. So the methodology is that first step, here n is equal to 6. So the minimum number of flip-flops, you can see here, put the element 6 less than 10 to the power 3. So 8 is now greater than 6. So therefore n is equal to 3. Number of flip-flops required will be 3. Now correct 3 flip-flops as a ripple binary counter sequence in the figure. The binary number for n is 110. The flip-flops for the output will be 1 at the count 110 are flip-flop 2 and flip-flop 1. So we can choose a 2-input NAND gate. Connect the Q outputs of the flip-flop 2 and flip-flop 1 flip-flop, that is Q2 and Q1, to the inputs of the NAND gate, and the NAND gate output to asynchronous clear input of all flip-flops. The counter clock counts from 000 to 101 until NAND gate output is high. But when it goes to state 110, all NAND gates input become high and its output will be low. Therefore, all the flip-flop will be cleared and it reset back to state 0, which is our objective actually. That at that particular count, the flip-flop should be cleared, or rather the flip-flop should be 000. So as you can see here, this is a mod 6 operation. So let's see here 0, 1, 0, another 1, 1, 0. Okay. So 1, 1, 0. So in this, so there is a binary equivalent of 6. Okay. So 1, 1, 0. Okay. So simply what you have to do, that you have to see here, as it is a ripple counter, this is a ripple counter. So 1, 1, 0, like this it goes. So these two 1, 1, that means this and this NAND should be taken and put to clear. Whenever that state will come, when there will be 1, 1, 0, then it will clear everything to 0. And this way the counter operation occurs. For ripple counters, the flip-flop used must be in toggle mode naturally. The JK or T flip-flop must be used in toggling mode by connecting JK or T flip to logic 1. Okay. Thank you.